In this video, we're going to derive an expression for the buoyant force on a submerged object, and then we'll apply that to a rock sitting on the bottom of a river. Then we're going to look at an expression for the buoyant force for a floating object and apply that to a floating iceberg. So we start with the submerged object, and just the basic physical principle here for why this thing feels an upward force exerted by the fluid is the fact that the pressure is greater as you go lower in the fluid. So down here, at a depth of D bottom, the pressure is bigger than up here at a depth of D top. To get the force exerted by the pressure, you just multiply by area, and so that upward force at the bottom is going to exceed the downward force at the top, leading to what we call the buoyant force. And so our mission here is to actually come up with what's called Archimedes Principle, which is just a really nice shortcut for finding the buoyant force on anything that's submerged or floating. I'll start by getting the force vectors in here for the force exerted by the pressure at the bottom. So I'll call that force sub little b, and that's going to be equal to the pressure at the bottom multiplied by the area of that face of the object. I then have a downward force exerted at the top, and I'll call that F little t, and that's going to be pressure at the top times the area of that face of the object. So let's put in the details at the bottom of the object. I have the force exerted upward is given by the pressure there multiplied by the area of that face of the object, and the pressure there is going to be rho g times the depth. And I should clarify that's the density of the liquid. How about the force downward on the top? F little t, it's going to be p t times a. That's going to be the density of the liquid times g times the depth of the top of the object times a. And then the buoyant force is this net upward force caused by the fact that the upward force on the bottom exceeds the downward force on the top. So I'm going to call that F capital B, and it's going to be that upward force on the bottom that was rho liquid g d bottom times a. All right, minus the force downward on the top from the liquid. And there's a lot of stuff that I can factor out here. So I end up with the density of the liquid times g times a times the difference in these two depths. So these depths are just measured as positive quantities, and I have d bottom, which is a larger number, minus d top, and I can see from the diagram that the difference in those two depths is actually the height of this object. So I'm going to rewrite it that way. And then I realized that in my expression, I have an AH. So that's the area of this thing multiplied by the height, which is the volume of the object. So finally, I end up with rho liquid times G times the volume of the object. And it might be fair to call that Archimedes Principle, but I want to go one step further and get something more like what Archimedes actually said. So the volume of the object is actually the volume of fluid that's been displaced here as I squished it underneath the surface. If I multiply that volume by the density of the liquid, well, density times volume equals mass. So these two things put together gives me the mass of the displaced fluid. If I then take the mass of the displaced fluid and multiply by g, I have the weight of the displaced fluid. And that's more like what Archimedes' principle actually says. The buoyant force is going to be equal to the weight of the fluid displaced when you submerge the object. Okay, let's apply Archimedes' principle now to an object that's submerged. So what I have here is a basalt cobble. Basalt is just the kind of rock that's rich in iron, so relatively dense. I gave it a specific gravity of 3.0 and a mass of 8 kilograms. And so it's sitting on the bottom of the river and, of course, submerged in water. And I'm asked to find the weight of this thing, the buoyant force on it, and the normal force on it. So notice before we start doing any of the math here that the buoyant force points up. So the water is sort of helping to lift up the rock a little bit. And that means the normal force is less than the weight of the rock. So we use the phrase apparent weight for that. And another way to look at it is it would be easier for you to pick up this rock if it's submerged in water than if it was sitting on dry land. I'll start by just popping in qualitative force vectors. There's the weight. Then I know there's going to be an upward buoyant force exerted by the fluid. That's going to be equal to the weight of the displaced fluid by submerging this thing in the water. And some normal force will still be required to hold this thing up against the force of gravity. So there's a bit of missing information here. I have that the mass is 8 kilograms. And the density, real quick, I get that from the specific gravity by realizing that 3.0, it just means 3 times as dense as water, so 3,000. But to find the weight of the displaced water here, I'm going to have to get the volume of the rock. Well, I can get that from the mass and the density. So just a quick reminder, density is mass per volume, which means volume is mass over density. So plugging in my numbers, that's 8 kilograms over 3,000 kilograms per cubic meter. And you can see that the units work out there. And I get a volume of approximately 0.00267 cubic meters. Now that was actually a repeating decimal, and I'm going to use the repeating decimal in my calculator so I don't compound my rounding errors. Okay, so now I apply Archimedes' principle, and I say the buoyant force is equal to the weight of the displaced fluid. So that would be the density of the fluid, well that's water here, times the volume of fluid that's been displaced. That will give me the mass of the displaced water. So that's the density of water times the volume of the object. I then take that mass, so this is the mass of the water that was displaced. I then take that mass and multiply by g to get its weight. So water is 1,000 kilograms per cubic meter. The volume of my object was 0.00267 cubic meters. And g, of course, is 9.8 meters per second squared. And when I run the numbers on this, I get 26.1 newtons. And I'll go ahead and put that up in my diagram as well. 26.1 newtons. Next, I'm going to get my weight for the basalt cobble. And that's a familiar calculation. I just take the mass and multiply by g. And for that, I get 78.4 newtons. Then finally, we're going to get the normal force, or the apparent weight, for the object. And that's a real simple force analysis. I know that the rock is just sitting there, so the forces must balance. And I could say it like this: all the forces upward better be equal to all the forces down. And that means my normal force cooperating with the buoyant force has to be equal to the weight. In other words, the normal force is the weight minus the buoyant force. Again, a little bit less than the weight of the rock. And that gives me 78.4 newtons minus 26.1 newtons. And when I run the numbers, I get a normal force of 52.3 newtons. All right, so I encourage you to try this the next time you're playing around the edge of a river. This is like a 30% reduction in the weight of the rocks. So if you try to pick up a large rock that's submerged in water, you can really feel the difference of how much easier it is to pick up. Now let's check out an object that's floating. So the first thing I want to do is look at it from the Archimedes point of view. And Archimedes' principle says that the buoyant force on this thing is equal to the weight of the displaced fluid. And then I start to wonder, well, what does this mean if an object is floating? It means it started to sink in the liquid until it got to the point that it displaced an amount of liquid whose weight was equal to the weight of the object. Well, since it took less volume of the liquid to do that than the volume of the object itself, that automatically implies that the object is less dense than the liquid. And that's a fact that you were probably already familiar with for objects that float. Things float if they're less dense than the liquid they're immersed in. So next I want to get into the actual calculation of the buoyant force for this object. Remember, the buoyant force is an upward force exerted on an object because the object is submerged or partially submerged in a liquid. For the submerged object, we had two forces to consider. Because the top surface was submerged, there was a pressure exerted downward on the top in addition to a pressure exerted upward on the bottom. This time is a little simpler case because the top is not submerged, and the buoyant force arises just from the pressure at that bottom surface, exerting an upward force. The force exerted by the pressure there is going to be equal to the pressure there multiplied by the area of the surface that pressure sees. Then I can plug in my formula for pressure at a depth in a fluid, and that's going to be rho times g times the depth, which I call d in this diagram. And then what I want to do is give a special name to this. d times a. If I look in the diagram, that means something geometrically. It's the volume that's actually under the surface of the water. So I'm going to call that V submerged. And I get that the buoyant force is equal to the density of the liquid times G times the amount of the object that's submerged, V submerged. So if I want to state it more like Archimedes stated it, I would say that submerged volume of this floating object, that's the amount of fluid that was displaced or pushed out of the way as the object started to sink. So that is the volume of displaced fluid. If I then multiply that by the density of the fluid, so I'm going to write it this way. It's volume of displaced fluid. So if I take a density and multiply by a volume, I get a mass. So I have a mass of displaced fluid multiplied by G, which again gives me the weight of the displaced fluid. So let's apply Archimedes' principle to the case of a floating object. And what I have here is a chunk of glacier ice that's broken off and is floating in the ocean. And glacier ice has a lot of air pockets in it. It has a density of 917 kilograms per cubic meter approximately. Seawater has a lot of salt dissolved in it, so it's bigger than the freshwater density. It's 1,030 kilograms per cubic meter. And what I want to do here is compute exactly what the tip of the iceberg is. So I want the percent of the iceberg sitting above the level of the water. So I start by getting into a force analysis. And gravity is pulling down on this thing with a strength of mg. And then it's in equilibrium, so the buoyant force must be equal to that. And I start messing around with the calculation. I say the buoyant force is equal to the weight. But I'm trying to get a percent of the iceberg sitting above the level of the water. So I want these things expressed in terms of volumes. So what about that buoyant force? Well, it's equal to the weight of the displaced water. So that's going to be the density of the water, not fresh water, but seawater, times the volume of water that's been displaced. Well, that's equal to the submerged part, the submerged volume of the iceberg, times G. Again, this density times volume here is the mass of displaced water. Just a reminder. And then the mass of the entire iceberg, well, that would be equal to the density of the ice multiplied by the volume of the ice. Again, that's the mass of all of the ice put together. And the weight, of course, requires me to multiply by G. So the G's are going to cancel out, and then I have a useful equation here because I can find a ratio of V submerged to the total volume. In other words, the submerged fraction of the ice, and that's going to be equal to the density of the ice over the density of the seawater, and that's 917 over 1,030. I don't care about the units because I see they're going to cancel. And this comes out to 0.89, or as a percentage, 89%. So 89% of the iceberg is beneath the surface. To answer the question, I wanted the tip of the iceberg, which apparently comes out to 11%. So the next time someone uses the phrase the tip of the iceberg, you know they mean 11%.